Millions of different chemical compounds are known. All of them are built from simpler substances called elements. Elements combine in countless ways, creating the millions of materials that fill our universe. Elements, substances composed of only one kind of atom, are the fundamental building blocks of matter. They combine to form chemical compounds, just as the letters of the alphabet can be combined to form words. The science of chemistry describes the behavior of substances as they undergo physical and chemical changes. Over 100 elements have been discovered. Each has a unique set of physical properties, like density and melting point, and each behaves a certain way in chemical reactions. But which elements will combine, and how? For centuries, scientists have asked these questions, theorizing and looking for patterns. From a mountain of data, chemists began to seek some unifying principle that would explain why different elements had different properties and different behaviors. The result? The periodic table, an enormously useful tool that scientists could use to discover, learn, and remember properties of the elements. With the periodic table and a basic understanding of how it is constructed, you can predict the properties of any element from its row and column. Elements that fall in the same vertical column on the table have similar chemical characteristics. Each vertical column is known as a group or family of elements. Some groups, like Group 1, are extremely similar, and other groups, like elements in Group 4, don't seem that much alike at first glance, but each group has a common set of characteristics. Horizontal rows are known as periods. A new row or period is started whenever patterns repeat. Let's look at it in a different way. The two rows that are set apart below can be inserted into the main body of the table. If we then roll the table, we see that where one row ends, the next begins. How does the periodic table work? Why do similar elements fall in the same column on the table? What gives elements their properties? The answers lie in the structure of atoms, the tiny particles that make up all elements and all matter. An atom is made up of a tiny nucleus comprised of neutrons and positively charged protons, surrounded by a cloud of even tinier, negatively charged particles called electrons. Because opposites attract, the negative electrons are held within the atom by their attraction to the positive protons. The atomic mass of any atom is the sum of the number of protons and the number of neutrons. The modern periodic table is arranged by increasing atomic number. An element's atomic number is equal to the number of protons in its nucleus. It also corresponds to the number of electrons in a neutral atom, because in a neutral atom there are an equal number of protons and electrons. Let's look at hydrogen. It occupies a unique position at the top of the periodic table and does not fit naturally into any group. Hydrogen has an atomic number of 1. That indicates that each hydrogen atom has one positively charged proton in its nucleus, which is balanced by one negatively charged electron. Why does all this matter? Well, in chemistry, it's the electrons that are important. Watch what happens when we bring these two hydrogen atoms in contact with each other. The electrons of both atoms are attracted to both nuclei, and a molecule is formed. A molecule is a collection of atoms bound tightly together. Electrons are the glue that form chemical bonds. And chemical bonds are responsible for all the substances we know and use in our world. The number and arrangement of electrons in an atom is crucial in determining how it will behave and how its electrons will bond with other atoms to make molecules. Helium, with an atomic number of 2, has 2 electrons in its atoms. What happens if 2 of these atoms come in contact? Nothing. The electrons in helium are held too tightly by the nucleus to be shared with another atom, so no bond is formed. The science of chemistry is the study of the properties of matter. These properties help describe the characteristics or personality of materials. The more we know about substances, the more new ideas scientists and engineers can come up with. Is it a solid, a liquid, or a gas? Is it hard or soft, shiny or dull? These are physical properties, characteristics that can be observed without any chemical changes to the material. Boiling point, melting point, scientists observe hundreds of properties in an attempt to get to know substances. But remember, in chemistry, it's the electrons that are important and how an element's electrons bond. Chemical properties describe the way an element behaves in a chemical reaction. But how exactly are the electrons arranged in atoms? And how does their arrangement affect an element's chemical properties? Think of electrons as being arranged in rings or shells around the nucleus of an atom. The farther away from the nucleus, the higher the energy of the electrons in the shell. If electrons are added to an atom, they fill the innermost shells first, and every shell above the first is actually split into a number of subshells, and they fill with electrons in a complicated sequence. Subshells are named by giving the shell number followed by a letter designation. The first subshell in a shell is called S, the second P, the third is D, and the fourth is F. For example, the lowest subshell in shell 2 is called 2s. The next subshell is 2p. The outer shell, called the valence shell, is most important in determining the properties of an element. Usually, chemical reactions involve valence electrons. The periodic table is divided into blocks based on valence electron configurations. Different valence shell configurations cause elements in different columns on the table to have different chemical and physical properties. The S-block elements all have the valence configuration S1 or S2. The P-block elements have valence configurations S2P1 to S2P6. The D-block elements have valence configurations involving D subshells. These elements are often called the transition metals. Differences between groups in this block are not as strong as in the others. But how can we explain trends in properties within the same column, as well as trends in properties across rows of the table? Again, the key to understanding these trends lies in the outer shell of electrons, the valence shell. Anything that affects the valence shell will affect the chemical and physical properties of the element. Let's look at the electron configuration for group 18, the noble gases. These are in the P block. Helium, with 2 electrons, has a stable electron configuration. So do the other elements in this group: neon, argon, krypton, xenon, and radon. Their outer shells are completely filled. There isn't any room for additional electrons, so these elements aren't very reactive. That's why they're called noble gases. The group used to be known as inert gases because it was thought that they never reacted with other atoms, but in reality, some do. The alkali metals found in group 1 of the periodic table are very reactive metals. They're S-block elements. Pieces of lithium, sodium, and potassium are stored in mineral oil or kerosene to protect them from air and moisture. Rubidium and cesium are sealed under inert gas. These elements may not look like more familiar metals, such as iron or copper. They are soft and have low melting and boiling temperatures. but they do share some characteristics with more familiar metals. As you can see, sodium conducts electricity. Because they all have only one electron in their outer shells, far from full, alkali metals are quick to bond with other atoms. In fact, they don't occur freely in nature because they are so reactive. In chemical reactions, atoms will gain or lose valence electrons until their outer shells are stable. This happens when they have the same number of electrons as the nearest noble gas on the periodic table. We can explain many of the reactions of alkali metals using this fact. For example, in this reaction, lithium is surrendering its valence electrons to water. Group 1 elements are called alkali metals because they produce alkaline solutions when dropped into water. The reaction produces hydrogen gas and a basic or alkaline solution, which can neutralize acids and turn litmus blue. We can place a dot next to the symbol for each of the alkali metals to symbolize the single electron in their outermost shell. All of the alkali metals have the same valence electron configuration as lithium, Ns1, where N is the period number. Since the valence shell determines how the element behaves in reactions, we expect all of the alkali metals to have reactions that are similar to lithium's. And here, we see that they do. Remember, the key to understanding the trends among elements lies in the valence shell. Anything that affects the valence shell will affect the chemical and physical properties of the element. Three factors are at work determining the size of the valence shell. The value of the principal quantum number for the valence shell affects its size. The larger the value of N, the larger the valence shell. The value of N for the valence shell of any element is easy to figure out. Just look at the period that the element appears in. Looking at the elements in group 1, we see that N increases as we go down the table. So lithium should have a smaller valence shell than sodium, although both have one electron in their valence s subshells. Potassium will have a larger valence shell than sodium, although again both have the same number of valence electrons. Nuclear charge also has a strong effect on the size of the valence shell. We know that protons are the positively charged particles in the nucleus, so the more protons, the higher the positive charge. And we also know that the atomic number equals the number of protons in an atom. So essentially, the atomic number is a measure of the positive charge on the nucleus. A higher positive charge on the nucleus will pull the negatively charged valence electrons inwards, shrinking the valence shell. The lower the atomic number, the larger the valence shell. The higher the atomic number, the smaller the valence shell. Since atomic number increases going left to right across the table, we expect the elements with the largest valence shells to be at the beginning of each period and the smallest ones at the end. And that's exactly how it is. Looking at the fourth period, potassium, atomic number 19, has a larger valence shell than calcium, atomic number 20. The higher positive charge on the calcium nucleus, plus 20 versus plus 19, pulls the electrons in its 4s valence subshell closer. Calcium has more electrons in its valence shell than potassium, so you might have expected calcium's valence shell to be bigger than potassium's. But adding electrons to the valence shell alone doesn't change its size much. Atoms with more core electrons tend to have larger valence shells. Because like charges repel, core electrons repel the valence electrons, pushing them farther from the nucleus. This effect is usually more subtle than the effects of nuclear charge and the effect of N for the valence shell. The halogens are 5 nonmetallic elements found in group 17 of the periodic table. The term halogen means salt former. Halogens exist at room temperature in all 3 states of matter: solid, liquid, and gas. Let's look at bromine near the end of the second period. Bromine has a total of 7 valence electrons, 2 in the 3s subshell and 5 in the 3p subshell. Krypton is the noble gas nearest to bromine. If bromine can gain 1 electron, it can attain a stable noble gas configuration. We can explain many of bromine's reactions using this fact. For example, if we bring bromine in contact with aluminum, the oppositely charged aluminum and bromide ions stick together to form aluminum bromide. All of the halogens are nonmetals, which means they are poor conductors of heat and electricity. All react similarly with hydrogen and with the alkali metals. How can we explain trends in properties within the same column, as well as trends in properties across rows of the table? One observable trend is in atomic radius. There is no practical way to measure an atom's radius directly, but we can estimate the atomic radius by taking half the distance between the nuclei of 2 atoms. As we proceed down a group or family of elements, say from lithium to cesium, the number of electrons in an atom increases, and as you might expect, so do their atomic radii. But as we cross a period from left to right, the radii generally get smaller. 1 electron and 1 proton are added to each element. The nuclear charge dominates and the atom contracts. This general trend is followed for most of the s-block and p-block elements. But we see some small irregularities in this trend with elements in the d-block. For example, going across the 4th period, we see a small decrease and then a small increase in atomic radius going across the d-block. Why? Both the nuclear charge and the number of core electrons increase going left to right across rows in the d-block. The increasing nuclear charge pulls the valence electrons closer to the nucleus, but the increasing number of core electrons pushes them away again. These two effects oppose each other. At first, the effect of increasing nuclear charge wins out, and there is a small decrease in atomic radius. But as more and more core electrons are added, the core electrons begin to win out. Another chemical property that can be observed with the periodic table is an element's ionization energy. An ion is a charged particle. In some chemical reactions, valence electrons are given up by one of the reactants. For example, in many of its reactions, sodium gives up its valence electron to become a positively charged sodium ion. This process is called ionization. Ionization energy is the minimum amount of energy required to strip an electron from an atom or ion in the gas phase. Atoms with low ionization energies tend to lose electrons in chemical reactions, forming positive ions. Atoms with higher ionization energies tend to share or gain electrons in a reaction. Let's look at trends in ionization energy. Overall, the ionization energy decreases going down a family. Why? The atomic radius gets larger as we go down a family, and so the outermost electron is more easily removed. The ionization energy also increases going across a period. The reasoning is the same. The atomic radius gets smaller, and so the outermost electrons are more tightly held and harder to remove. Ionization energies can help explain an element's chemical behavior. Metals tend to lose electrons in their chemical reactions and have lower ionization energies. The most metallic elements are at the bottom and left sides of the table. Ionization energies for elements on the top and right sides of the table are higher. These elements are nonmetals. can use the trends in ionization energies to explain why some elements are metals and some aren't. The ionization energy of metals is very low. They lose valence electrons so easily that valence electrons are shared among all of the neighboring metal atoms. About 3/4 of all known chemical elements are metals. Metallic elements are essentially positive ions bound in a cloud or sea of valence electrons. This sea of electrons gives metals their characteristic properties. Metals are usually shiny, dense, crystalline solids that conduct electricity and heat. Typically, the atoms of metals contain less than half the full complement of electrons in their outermost shell. Because of this characteristic, metals tend not to react with each other, but do react with nonmetals. As we move from left to right across the table, the elements gradually become less metallic. Magnesium and aluminum are metallic, but harder and less reactive than sodium. Silicon is a metalloid, an element with a blend of metallic and nonmetallic properties. Elements to the right of the stair step are nonmetals. The metallic character of the elements increases going from top to bottom and from right to left on the periodic table. This is an example of periodicity, regularly occurring similarities in properties of the elements. Metals can be hammered into different shapes without breaking. That's because the positive ions in the metal can slide past each other, but still remain bound by the electron sea. The mobility of electrons in the electron sea explains how metals are able to conduct electricity and heat so well. If we push an extra electron onto a surface of the metal, it displaces nearby electrons, sort of like a domino knocking down others in a long line. This passes energy, heat or electricity, easily through the substance. We've seen that many chemical and physical properties of the elements have to do with their electron configurations, and the valence electrons are the most important. The regular variation in properties, such as atomic radius and ionization energy, is a direct result of regular variations in the number of valence electrons. These variations are fundamental in understanding the structure and behavior of all the elements that make up the universe. Group has a common set of characteristics. Horizontal rows are known as periods. A new row or period is started whenever patterns repeat. Let's look at it in a different way. The two rows that are set apart below can be inserted into the main body of the table. If we then roll the table, we see that where one row ends, the next begins. How does the periodic table work? Why do similar elements fall in the same column? Each has a unique set of physical properties, like density and melting point, and each behaves a certain way in chemical reactions. But which elements will combine, and how? For centuries, scientists have asked these questions, theorizing and looking for patterns. From a mountain of data, chemists began to seek some unifying principle that would explain why different elements had different properties and different behaviors. The result? The periodic table, an enormously useful tool that scientists could use to discover, learn, and remember properties of the elements. Millions of different chemical compounds are known. All of them are built from simpler substances called elements. Elements combine in countless ways, creating the millions of materials that fill our universe. Elements, substances composed of only one kind of atom, are the fundamental building blocks of matter. They combine to form chemical compounds, just as the letters of the alphabet can be combined to form words. The science of chemistry describes the behavior of substances as they undergo physical and chemical changes. Over 100 elements have been discovered. With the periodic table and a basic understanding of how it is constructed, you can predict the properties of any element from its row and column. Elements that fall in the same vertical column on the table have similar chemical characteristics. Each vertical column is known as a group or family of elements. Some groups, like Group 1, are extremely similar, and other groups, like elements in Group 4, don't seem that much alike at first glance, but each column on the table. What gives elements their properties? The answers lie in the structure of atoms, the tiny particles that make up all elements and all matter. An atom is made up of a tiny nucleus comprised of neutrons and positively charged protons, surrounded by a cloud of even tinier, negatively charged particles called electrons. Because opposites attract, the negative electrons are held within the atom by their attraction to the positive protons. The atomic mass of any atom is the sum of the number of protons and the number of neutrons.